Hey everyone, welcome. You know, in math, it's really all about having the right tool for the right job. And today we are unlocking an awesome one for understanding those beautiful curves we call parabolas. So let's just dive right in.
So let me ask you a question. When is the landing actually more important than the flight itself? I mean, think about it. If you're launching a rocket, or even just throwing a ball, sometimes what you really care about isn't how high it goes, but where it starts and where it lands. That's the exact idea we're going to tackle today.
Look, I'm sure you've probably graphed parabolas using vertex form or standard form before, and don't get me wrong, they're great. They are fantastic tools. But today, we're zeroing in on a specialist, a form that is an absolute rock star at finding those ground points. You know, the start and the finish.
So let's meet our hero for the day, Intercept Form. The amazing thing about this is that just by looking at the equation, you can instantly see where the graph crosses the x-axis. Seriously, no crazy calculations needed for that specific piece of info. It's just right there in the formula. That's its superpower.
Okay, let's break this down. What's so cool here is how it all just flows together. See those p and q values? Boom, those are your x-intercepts, your two ground points. And since every single parabola is perfectly symmetrical, right, the axis of symmetry, that center line, has to be smack dab in the middle of them. And once you know that center line, well, you've got the x-coordinate of the vertex. You just plug that number back into the equation to find out how high or low it is. It's such a simple, elegant process.
All right, that's enough theory for now. You know the best way to really get a feel for a new tool? You got to use it. So let's walk through a couple of examples, step by step, and see how we can turn these equations into actual graphs.
Okay, here's our first one. We're going to follow a super simple three-step process. Step 1, find where it hits the ground. Step 2, find that center line. And step 3, find its highest or lowest point, the vertex. Ready? Let's do it.
Okay, step 1 is finding the intercepts. It's so straightforward. You just take each little piece in the parentheses, each factor, and set it equal to 0. So if x plus 2 equals 0, well, x has to be negative 2. And if x minus 4 is 0, then x must be 4. And bam, just like that, we have our two landing spots, negative 2.0 and 4.0.
Now for step 2, the axis of symmetry. Remember what we said? A parabola is a perfect mirror image. So that center line has to be exactly halfway between our two intercepts. All we have to do is find the average. So negative 2 plus 4, that's 2. Divide that by 2, and you get 1. So our vertical line of symmetry is right at x equals 1.
And for our final step, let's find that vertex. We already know the x-coordinate is 1, right? So we just plug that value back into our original equation. We get negative, 1 plus 2 times 1 minus 4. That simplifies to negative 1 times 3 times negative 3, which gives us a positive 9. So the highest point of our parabola, the vertex, is at 1, 9. Done!
Okay, you ready for another one? This one looks a little different. You might be thinking, hey, wait a minute. Where's the second set of parentheses? This trips people up all the time, but trust me, it's actually even simpler than the last one. So the two factors here are just x and x minus 6. Think about it. If that first factor, x, is 0, then, well, x is 0. Easy, right? The other factor, x minus 6, gives us x equals 6. So there you go. Our intercepts are at 0 and 6. And the midpoint? I think you got this. Halfway between 0 and 6 is, of course, 3. And just like before, we just plugged that x value of 3 back into the equation to find the y-coordinate of our vertex. Let's see, we get 2 times 3, that's 6, times 3 minus 6, which is negative 3. So 6 times negative 3 gives us negative 18. Wow! So our vertex for this parabola is way, way down at 3, negative 18. Okay, I think you're ready for a challenge. Let's flip this around. What if we don't have the equation? What if all we know are the landing spots and, say, one other random point on the curve? Could we build the equation from scratch? Oh yeah, we bet we can. So here's the game plan. We're going to start with the basic skeleton of the intercept form, and we'll plug in the intercepts we know, negative 1 and 5. Now remember to flip the signs. So that gives us y equals a times x plus 1 times x minus 5. The only missing piece of the puzzle now is that a value, and that's where our other point comes into play. It's pretty cool, watch. We take that point we know, 2, negative 9, and we just substitute the x and y values into the equation we just put together. So negative 9 goes in for y, and 2 goes in for x. Now, a is the only thing we don't know. A little bit of simple algebra here. Negative 9 equals a times 3 times negative 3. So negative 9 equals negative 9a. Well, that means a has to be 1.
And since we solved for a, we can now write our final, complete equation. The parabola that crosses the x-axis at -1 and 5 and also passes right through the point 2, -9 is simply y equals x plus 1 times x minus 5. And we're done. Pretty neat, huh?
Okay, listen up, because this next part is really important. Using this formula is pretty easy once you get the hang of it, but there are a couple of common traps that are just as easy to fall into, so let's talk about them so you know exactly how to avoid them. Okay, pitfall number 1, and this is by far the most common mistake. It's all about the signs. It is so tempting to look at something like x plus 2 and think the intercept is at +2. But no. You gotta remember, you're solving that little mini equation, x plus 2 equals 0. And that means the intercept is at -2. So, my advice? Always, always, always remember to flip the sign you see inside the parentheses.
And the second big pitfall is forgetting about a. You know that little number hanging out in the front? It's not just for decoration. It controls everything. It tells you if the parabola opens up or down, and it handles the stretching or squishing of the whole curve. If you forget to include it when you're calculating your vertex, I guarantee your answer will be wrong every single time. So please, whatever you do, don't forget a.
So you might be wondering, okay, why are we spending all this time with these P's and Q's and A's? Well, it's because this isn't just some abstract math problem in a textbook. Let's take a look at how this exact formula is used to build incredible things in the real world. This is one of my favorite examples. Just picture a huge suspension bridge, like the Golden Gate. The two giant towers, those are the anchor points. For all practical purposes, they are the x-intercepts of that big hanging cable. The engineers know exactly where those towers are going before they do anything else. That's ground zero for the whole project.
And here's where it connects directly back to what we've been doing. If the bridge spans, say, from 0 meters to 100 meters, that gives engineers their starting equation, y equals a times x minus 100. The only thing left to figure out, that a value, is determined by how much they want the main cable to sag in the middle. And guess what that lowest point of the sag is? Yup, it's the vertex.
So you see, once you know what to look for, you start seeing these parabolic curves everywhere. The arc of a basketball shot, the shape of a satellite dish, even economic models for revenue. They all have starting points and ending points. They all have these beautiful curves that are just waiting to be solved with the exact tools that you now have in your toolkit. So the only question left is, what are you going to solve next?